Sure. So yesterday I didn't like I couldn't prepare the PPTs. I had a lot of work from my company,
Okay, okay.
so I had to go like a scratch pad kind of thing. Okay, I
Mm-hmm.
know I made a mess there.
Okay, no issues, no
So
issues.
let's just revise it like super fast. Okay, whatever happened yesterday in a structured way, and then we can go ahead with the today's topic. So fine.
Yes, 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 fine, sure.
So yes, so yesterday we were speaking of the timeline, right? The ages of AI. So basically starting from 1960s to 1990s, right? First of
Yep.
all, considering the basics, artificial intelligence, when said, it's more of an umbrella term. So let's say AI is the whole umbrella term within which
Mm.
machine learning is a subset. Hello.
Yeah, you can continue, you can continue.
Yeah. So machine learning is a subset of AI, and within which deep learning is again a subset of machine learning. Although these are like the part of AI, but they are more specific. It gets like uh, it's more specific within the AI itself, right? So
Mm-hmm.
yesterday we were speaking of this. We kind of understood with the different examples what make the difference between like the umbrella term AI and the machine learning. What does it solves, and what does the deep learning solves, and what is the need of all such, right?
Mm-hmm.
So we'll be moving further with this actually. Okay. So yes. So first, let's understand like what is artificial intelligence. That's the definition says. Okay, any technique that enables a machine to mimic a human intelligence. Let's say there is a machine which is like acting like a human. There is nothing but artificial intelligence, right? So there is an intelligence which we are looking at, which is artificial, which was not natural, right? So that is what artificial intelligence actually means, right? So it could be in this session, I'll be taking up like one single example, and we will look at that particular problem and try to solve it through ages of like AI. Okay, how the if else conditions would have solved it, how the machine learning would have solved it, or the deep learning would have solved it, how it is
Okay,
being solved now. Okay? So that we'll be consistent with the example, and also we could understand the techniques better.
okay.
Yes. So a rule-based technique we will look at like the if else conditions. Okay. So let's just say there is a problem statement where with the image given, whenever an input image is given, we have to identify whether it's a cat or not. Okay. So if we are supposed to write if conditions for this, so how many if conditions there would be? Let's just say we are looking at some kind of condition one, which actually mentions ears. So ear is kind of for cat, ear is pointy or sloppy like such, and their conditions comes in fur type, usual colors, all these if conditions, right? There could be a number of if conditions, and we write all this. So the face may be like a triangle kind of thing. There could be a condition. The size of an animal, yes. So is it an domesticated? Yes, right. It's a pet basically. All this. So there could be like n number of if conditions, and even then, consider we have given all the inputs, and then this picture comes in. So whatever the image is here, it's been shown, right? So naturally, we can say that this could be like most probably it's a cat, right? We can't be definite even with our senses. This could be a cat, probably, right? So we can't consider, and if we can't cover up all the if conditions here, right? Although we may write up like if conditions for lot of if conditions, we may not cover up like whole condition within this environment, right? So imagine the input image is a cat, but from the front angle, it's from the top angle, it's from the bottom angle, it's from some hidden camera or something like that, right? So all those if conditions we can't write. So this was the problem with if conditions. Okay, if else uh, like this is also an AI because it is capturing conditions and it is giving us intelligence, right? If this happens, run this code. If this condition satisfies, run this code, right? But still, here we have to write every pixel of this particular image. let's say this image is divided into like multiple pixels, right? So in each pixel, we have to write an if condition for all this, and that's kind of not possible, right? And this may change every time the image changes. So this was the problem with if else conditions, the starting of AI, where it was like 1960s to 1990 kind of thing, where we were stuck. Actually, it's like 40 to 50 years we were stuck. And then the machine learning was introduced. So machine learning, instead of like we put up the condition, we thought, let's put up a data. Okay, let's put up, this is the data we have. Okay, for this data, we have got this particular answers. Okay, so let's just say we have a lot of images and all the pixel data we are listing it. Okay, and then we are saying whether it's a cat or not. Cat, not, right? So this is what supervised learning yesterday we were discussing. We considered the example of emails, spam or not spam, right? So here, instead of saying this condition happens if this condition, that's only cat. If this condition, that only cat. So condition one, condition two. We are letting know a machine the inputs, the characteristics, and what it should know, like the target. Okay. So here, so basically, we are not preparing the rules. In if conditions, we were actually writing up the rules, right? So in machine learning, we are giving it a data, we are giving it an answer, and we are asking it to like consider its own rules, uh, right? It can generate its own rules, try to understand the statistical patterns from that particular input, and to get that particular answer. And then it can consider like make some rules, rule one, rule two, rule three, and then within that rule, it can in the next input, it can predict a probable whether it's a cat or not, whether it's an animal or not, whether it's an spam or not, email, right? So that's what machine learning was about. So yes, so machine learning are of like three kinds. Okay, individually they are divided into like 3 points. One is supervised learning, where there is input, characteristics is being given, and there is a guided output. Human is saying whether it's a cat or it's a dog, it's a cat, it's a dog. Okay, for these particular conditions, whatever the target is, that is the answer. Human is guiding this this model. So that type of learning, that of machine learning is called supervised machine learning. While unsupervised is yesterday I told you, right? So there are like this is for organizing the things. So there is an horror, there is an drama, there is an romantic bookshelves. Okay. So whenever a new kind of book comes in, so machine has to identify where this particular book one suits, and it has to classify. Let's say it is an book one is an romantic book. It has to be classified into romantic section, right? So this is here we are not giving it an answer, but we are letting it know the data, and depending on which it is trying to classify the things. Okay. So this classification rules we are not providing it. It is itself is trying to understand the boundary between these three sections. Okay. So these are so unsupervised learning models. And the last one is reinforcement learning. So a classical example for reinforcement learning is, so what is reinforcement learning anyway? Let's understand that first. So it's a trial and error kind of thing where the model tries to predict something. Okay, let's say prediction one happens, and let's say this is a wrong prediction. Then the model tries to understand why it is a wrong prediction, and in the next time it tries to predict two, and it tries to predict the like different probability, and it actually recorrects here. Okay, so this recorrection, so this is it is trying since it didn't work out, it is finding that error and it is retrying again. It is trying to resolve its own like drawbacks. So this is reinforcement learning. Where does this like what is the example for this is? So whenever you are writing up some like as you are using Google keyboards, right? So there are like three for every statement you are writing, there could be coming a next word prediction, right? So probable predictions. So among which, like let's say you are speaking in mother tongue, but in English. Okay, we always do it in WhatsApp kind of chat applications. So there are standard words that are supposed to be used, but since you are using your mother tongue, you may use something rather else than this, right? So here, the reinforcement model, what it is doing is, although I've suggested these particular prediction 1, prediction 2, prediction 3 words, the user is not choosing any of it and it is typing its own. Okay. So it is recorrecting its training. Okay. So now in the next iteration, after a while, whenever you are writing a statement, it would suggest something which you usually use. Okay. It was not the original characteristic of this model, but it adjusted as per the user needs. Okay. So this is customizing a user experience, you can say. For these kind of applications, for these models are basically like reinforcement models. They are trained on like the reinforcement learning. Okay. So all the AI chess games, so where the computer plays, or any of the games where computer plays, right? So that is nothing but reinforcement learning in action actually. So these were the three different types of machine learning models. We don't need to like get into the depth of this, but it is since we are trying to understand the AI, so it is better to understand the technical gist of like all these things, as these will be coming up as an overview of this particular machine learning. Whenever someone say machine learning, so they should be at least knowing this. So this is an overview. Okay. So underneath, it's machine learning is using statistics. Okay, in order to predict whatever either it's a supervised model in the training or in the unsupervised model in the training. So underneath, everything is in statistics. Okay, and through the statistical analysis is trying to give out the answer. Okay? So that's the gist of machine learning models. So we'll just move ahead. So now comes the deep learning age, that is 2010 to present, right? So let's understand what's happening here. So this is, as the word says, right, deep learning. So it internally uses basically the neural network. It's written here somewhere. Yeah, artificial neural networks. Okay. So as we know, our brain is made up of like neurons. Okay, it's in combination of electric signals. So whenever our sensory organs, let's say eyes, okay, whatever it is seeing with the visuals are passed to our brain through these neurons. Okay, and there are electrical pulses happening, and these electrical pulses are being recognized, and there is a visual image that's being formed. That's what like whatever we are seeing. Okay, so internally that's how our brain, our eyes do see the things. Okay, so we are trying to mimic this. We are trying to artificially create this environment. Okay, so that is what deep learning was about. So basically, we are trying to create artificial neural network. Okay, and so the idea was to create these artificial neural networks and let it be exposed to the data. And as our brain is trained to find the patterns out of the world, right? To understand it better. So using this, we may better understand the patterns. Was the idea of like introducing this? Okay. So internally, it's a deeper set of like machine learning model. Okay. So neural network is completely made up of neurons. Okay. So neuron is basically a machine learning model where it takes an input and it tries to classify the output, yes or no, maybe. Okay.
Yeah, I have a question here.
Okay.
So, in the deep learning, when we talk
Mhm.
about neurons,
Yes.
basically these neurons are some software code only, right? Which are running on some high-end processors and GPUs. Like,
These neurons are actually machine learning models itself. Okay.
okay.
So they use statistics in like internally, okay, in order
Mhm.
to try to understand a pattern. And just like machine learning models, how they were solving the problem, these each neurons are capable to solve a particular problem. Okay.
Okay, so each neuron is kind of a model,
Yes.
and
Yes.
the
Yes.
group of neuron, the interaction between the neurons, or in other words, the interaction between the models are called deep
Yes.
learning.
Yeah. It's
Like
kind of
each neuron is
similar.
capable of calculation, and each neuron is capable of analyzing their own analysis.
Right, right, right,
Okay.
right. So let's say, so this is a machine learning model. So that's a neuron. Okay, it is taking up an input and it is completely capable of doing the machine learning tasks. Okay, so what we did is, so each particular node you are seeing in this image, right? So there are like number of nodes, right? So each node is a neuron. So let's say these are like machine learning models in itself. Okay. So we are connecting each of these interconnected. They are interconnected like web kind of thing, where we are providing inputs to all these nodes, the first layer. Okay. And then they are predicting something. They are trying to understand a pattern. Okay. They are trying to understand some pattern. All these. Okay. And then these patterns are being passed to the new input is being passed to. This is not the original input anymore. This is the output of these neurons. So these are passed to this second layer of neurons. Okay. So they will take this as an input. So all the responses from these particular models, and then they try to figure out some pattern out of it, and then they give out output, and these are fit into like this third layer. Okay, so how many layers would there be in a deep learning neural architecture? There could be like n number of layers. Okay, so usually, so this is an input layer where the raw input of is given input layer. Okay, so the last layer would be output layer,
Arya,
and in
is it
yes,
possible that the deep learning model can go into infinite thinking? Like there is no output, it's just analyzing, and prediction and coming output, and then prediction, coming output. It goes in the infinite thing. There is no output
no,
coming
not
out of
actually.
it.
No, that can't happen because each machine learning model is trained to it is trained to predict something out of it. Even though it may be like let's just say there's a dog or cat prediction. Okay, even though there isn't like 0.5% of like dog prediction.
Okay, Arya, what I'm thinking is let's understand a kind of scenario where you
Hmm.
gave let's talk about the first level of neurons. You
Okay,
ask them to just give me a random number from 1 to
okay,
infinity,
okay,
and every neurons came out to be some random numbers. And
right.
then moving forward, they provide these random numbers to the next level of neurons. They're
Hmm.
again thinking, okay, not this random number, let me give the another random number, a unique one, kind of prime number or something. Then these
Okay,
they give output to another level, thinking that okay, let me give some more unique. So just they are not converging towards a common solution. They are just going on kind of infinite level of thinking. So is it possible? Because when there is no finite answer, they can go into infinite thinking. Is it possible or not? When there is no
right.
finite output, let's say if I give, if I ask you, if I ask them, give me what is the answer for 2 multiplied by 2, the answer is 4.
Okay,
But when I say that, give me a random number, in that
hmm,
case, random number can be anything.
right.
When they start going inside, they become, uh, they can think of something like which is not a solution.
Okay,
So what about this? Like deep thinking going in too deep that it's not coming out. Like, is it
okay.
possible?
So yeah,
Is there a
maybe
term in deep learning?
let's just look this problem in different perspective. Okay,
Mhm,
so what is the deep learning is trying to solve? It is trying to understand pattern out of the given data, right?
mhm.
It is not actually like the predicting a random number is not in the training data. If it was
Yes.
trained on a data where that particular person is being given with the like characteristics of these particular things, and then the number has to be generated. So we need to understand creating a random number or generating a random number is not actually like we are speaking of a training a model, training a machine through the
Mhm.
input data. Okay, but predicting a random number is completely like offset to this particular topic.
Okay, okay.
Like, yeah, that's a problem. Yeah, definitely, generating a random number is a problem to be solved, but it is not with the context of like the deep learning. So that's the problem of its own.
Mhm.
So it is not completely related to like for this particular topic or the concept we are discussing. Maybe the question asked is completely off.
Okay, we'll ask this question to one of the AI only in future.
Okay.
Okay.
So so this deep learning, what it's trying to do is, in order to get a particular output, so it is trying to understand deep patterns. Unlike machine learning usually goes for like statistical analysis, while deep learning, since it is in set of like machine learning models, uh, the pattern identification goes much deeper. Okay, so let's imagine, let's take up an example to understand this better. Okay. Let's just say there is an like a set of cat images that's been given, cat and dog images. Okay, the classical example. So the first layer may identify, uh, whether like the facial shape, maybe whether it's a square, rectangle kind of thing, the ears or the edges. Okay, this could be characteristic, character one, character two, character three, and the size of it maybe okay, character four, and maybe the whisks, so the mustache the cats do have, right? So all this like C5, character 5, anything, okay? So these could be the set of characters this particular first layer is trying to identify, okay? And then comes the second layer. What it is trying to identify is it is going much deeper. So it is getting into like ear shape. So how does the color blending happen there in the picture? Or how is the eye color, how does that eye matches the eye pattern, okay? Does it have got like nails, does the tail is big enough? So more intricate patterns, right? So as we go deeper, these hidden lists, so basically, yeah, I missed it. So first one is the input layer, the last one is output layer. All the layers in between are considered to be like hidden layers. Okay, these hidden layers could be like one layer or two layer or n layers. Okay, so the more the number of layers, the more deeper the pattern identification goes in. But yes, the computation also increases. The time taken for the output also increases with it. Okay, that's the trade-off. But yes, so the number of hidden layers, it is trying to understand much more deeper pattern into the input from the input, and it is trying to give an output. So basically, that's why for this particular reason itself, deep learning neural network models, they are data hungry. Okay. Let's say they have like 1,000 or 10,000 rows of data, cat images and dog images. You may train a machine learning model with it, but for a deep learning, you may need like lakh or 10 lakh. Okay. More like 10 times or 20 times or 100 times the machine learning model what it needs. Okay. So it understands all these patterns. So that's why whenever you have like less data, machine learning models work way better than the deep learning models. But when you have more data, deep learning models definitely beats the machine learning model. Okay. So it's on like how much data do we have. So these hidden layers, that's what it is trying to identify. The first layer may identify the more common features. The second layer may identify more intriguing features. And the third layer may identify like something specific. So we don't know what these patterns identifications are happening because we have to understand one thing. So there is an application, there is an input, there is an output. Okay. So when we know this input is being processed in certain way, okay, some a plus b whole square is happening. Okay. And there is a formula that's being run and there is an output. This is the usual Python functions we write, right? So if this happens, we know it's happening, what's happening in this basically the application box. Okay. But when you give an input and you don't know what's happening here, but you are getting an output by some means. Okay, you don't know how the output is being given. So these are called like black box models. Okay, so and even though machine learning, the complex machine learning models like maybe random forest or XGBoost algorithms, these are again black box models. But deep learning models, most of the deep learning models are black box model. We don't know how they are recognizing because, as I said, what's the second layer or the third layer is trying to identify the pattern. We don't know what it is trying to identify and what it is actually identifying. Okay, but it is identifying something, and we are getting the desired output for it. Okay, we are happy with the output. Okay, it is easily recognizing the cat, what's the cat is and what's the dog image is, but we don't know how it is doing it. Okay, we can't identify it. So that's why they are called like black box model. We can't explain these particular although I'm explaining it. So whenever you are training a model, you can't directly explain this layer is doing this particular thing, this layer is doing this particular thing. This is an analogy which I am providing it. Okay. So this is what deep learning models are. So deep learning models are data hungry. This is you have to remember this. This statement is like way too valid for deep learning models. Any doubts until now before going ahead?
Uh, yeah, so current AI, whatever we have, whether it's a generative AI or
Mhm.
anything, so they are running on deep learning model, is it?
Right,
Is it
right,
statement correct? Okay,
right.
okay. And is it kind of deep learning model is what we see in the future also, or is there something parallelly which is going on which is more powerful than a deep learning? Like, what do you see? Or it's a
No.
kind of a consistent one?
Okay. So yes. So deep learning models. So are subset of like machine learning models. Okay. So there
Hmm.
are particular set of algorithms which are again all the deep learning models are machine learning models, but all the machine learning models are not deep learning models. That is the like superset or subset of, right. So
Hmm.
yes, similarly, generative AI is actually the concept where it is using transformers, and
Okay.
as you can see here, transformer architecture itself is actually a deep learning model. Okay,
Okay,
it's a
okay,
part of
okay.
like deep learning model.
We are
So
moving inside the deep learning model now.
yes, so generative AI is actually a subset of these deep learning model again.
Hmm.
Okay. So yeah,
Okay.
we will look into this. We will just explore the types of deep learning models and what are these actually usually used for, and then we can move ahead with the GenAI. Okay. Yep. So CNNs. So there are majorly three types of deep learning models. So CNN, uh, convolutional neural network, RNN, recurrent neural network, and transformers. So all the generative AI, whatever we are seeing, so that's because of the transformer sake. Okay, this is the latest discovery too. It's just around 2017. This the first research paper on transformers was released. Okay, so let's understand like these two before going into transformers. CNN and RNN. So what does they mean actually? So CNN. It is type of deep learning algorithm which specializes in like image and video processing. So yesterday we took up an example of like traffic police, traffic cameras, right? So where it identifies the vehicle number, it identifies the helmet if it identifies the seat belts. So internally, CNN is being in use. This particular algorithm is in use. So where it is specialized in understanding image, recognizing the images and the videos, and it is fully the grids basically. Okay. And yeah, the classical example of CNN, you would be like amazed. All your facial recognition feature in your smartphones, right? So that is CNN in use. Okay, that's why even though in the good lighting you may have taken registered your facial expression, but even in the low lighting, or even when you are sweating, or even when you are like dripping or something like that, even though that's the case, it identifies it. Okay, though that powerful CNN models are. Okay, that's the classical example of CNN models, usually image and video data. And RNN models, the recurrent neural network. So these are like text-based deep learning models where it is used for like sequential generation, word generation. Okay. So we could take up an example of like just how we took an example of Google keyboard, right? So continuously you are typing in and you are trying to predict something. So these recurrent neural network are actually used for like sequential data. Let's just say stock market analysis. Okay. So the time matters there, right? Let's just say you have to predict something time based, okay, or something linear. Okay, it is based on something. Okay, maybe it is based on time or the value or such. Okay, so then this recurrent neural network comes into play. Okay, or so as said for a word order, next word prediction. So basically, so let's just say designed. So whenever you are writing design, it's usually the next word would be like for or designed by, right? These words. So in order to predict these words, the order matters. First, it has to be designed, then only the for or is or by can come in, right? This order. For such tasks, these recurrent neural networks are in use. And as of transformers, so this is an important point. The GPT, okay, chat GPT. So T actually stands for transformers. And all the generative AI models, what you are looking at, are based on this particular transformer architecture. Okay. We shall get into the transformer architecture and we'll try to understand what transformer architecture is too. Okay. Yeah, that's the gist and basics of like the whole AI. Okay. Yeah, this is about like the deep learning models being black box models. Okay. We don't always know why the AI made a decision. Our job is to build and testing system. So yes, since they are black box models, that's why the role of AI quality engineer comes in. Okay, that what makes it like more non-deterministic. Okay, even though it may so let's just say in a classical software engineering job. Okay, let's just say an API. It was supposed to be so. This is an Gemini or ChatGPT OpenAI API, and it was supposed to respond with a JSON object. Okay, although it may respond JSON object for like 999 times, but it may fail in the thousandth time because it is a black box model. Whether where it is making a mistake, we don't know. And this is what non-determinism is, right? So this is why the need of AI quality engineer comes in. Okay. So does that summarizes everything and gives you like more clear picture of what we are trying to discuss and what we discussed yesterday? So any doubts until this point?
Hi, Arya.
Trying to speak like yeah, yeah.
Am I audible?
Your voice is too low actually. Saurabh, is it audible to you like clearly?
No, no, it's feeble. Maybe you can try speaking louder or just adjust your microphone.
Okay, okay. How about now?
Yeah, that's better.
Okay. So, general
Yes.
question from my side.
Okay.
So in this deep learning is majority consists of like images, videos and all, or what are the other scenarios that we usually see using deep learning?
So yes. So we have specific. So we discussed on specific type of deep learning models, specific algorithm that is convolutional neural network. Okay. So these
Mhm.
actually are expert in videos and images. But
Right.
as of RNNs, that is recurrent neural network, these are better with stock prediction kind of thing, or let's just say rain prediction, weather prediction, where something is dependent on timeline. Okay, there is an
Okay,
order.
okay, okay.
Let's just say there is an we have need to create a sentence formation. Okay, so
Kind of like a
whenever I'm
mathematical
say I am,
pattern. Is it like RNN is kind of a mathematical pattern where some formula is applied?
no actually,
Okay.
so no, so mathematical pattern. So yeah, it is definitely trying to understand a pattern, but it is good at wherever there is an order. Okay, like this has to be the first task. So the next is the second process. So second process can't go without the first process, right? Wherever things are dependent on the previous whatever being generated or whatever is there. Okay. In those tasks, like whenever you are writing a statement, I am, maybe you can say like good boy, right? Or good girl. So the word matters here. If I change the word, let's just say goodbye, I am. It doesn't make sense, right? It doesn't make an English word, English statement.
Yes.
So wherever this order matters, there this RNN is good. it's the best in deep learning model. And we have like transformers also, which actually uses attention mechanism. I just don't wanted to like explain transformers here itself. That's why I tried to like skip it. Uh, so we will have a complete session on transformers where it actually uses attention mechanism kind of thing, where it like we will explain more on this architecture. Okay, in
Okay,
today's session
sure.
itself maybe. Okay,
Sure,
so
sure.
these are like type of deep learning uh, like models. Did I answer your question?
Yes, yes.
Sure.
Thank you.
Any other doubts? Okay. Sure. So yes. Oh, sorry. Okay. So let's understand more on this term. What usually the general public says as AI, and what the people who knows AI actually call it as like large language model or LLMs. Okay. So yeah, so under the hood, how these work and what are the important things we need to like know about these large language models. Let's understand this. So this was the main topic of today, but yesterday since it was a scratch part kind of thing, I wanted to explain and clear the things better. Hope it worked. Right. So since all the deep learning models were already black box models, they are like black box. We don't know what's happening inside, but we are giving some input and it is trained. It has identified the pattern. It is giving us some output and we are satisfied with this output. Okay, not always, but most of it. Okay. So here, what's happening? Logic. Yeah, it's more of a magic. Although it's a logic, we just don't understand it. And whenever we don't understand some logic, we call it a magic, right? So let's try to understand more gist of like what's happening here in this black box model. Although we can't explain every model we train on, but we know like how these models are trained and how it is trying to recognize the things. Okay, let's understand that part of it. Okay. Okay. So this is on like how this OpenAI or Gemini. Okay, all these large language models. Whenever you're getting some giving some input, some prompt. Okay, you are giving some instruction basically with a prompt. It's nothing but instruction. So whenever you are getting giving this instruction, how it is actually understanding this, uh, right? So yesterday I told you. So these large language models doesn't understand English or any other languages, right? So then how is it understanding your prompt instruction? So I also said, so our instructions are being converted into like some mathematical vector forms. Okay, some mathematical representation, and it is internally it's all maths, right? So we will try to break down more on this now as of today's topic. Okay. So in order to understand this better, so how this everything is happening, so we have to understand a few terms. Okay, that is tokenization, embeddings, and transformer model. Okay, so this is transformer architecture, which we will look at. So the tokenization and embeddings, we will understand what it is. Okay, first tokenization. Okay, so this is in general sense. Okay, so one token is of like 0.75 of the English words. So this is for English words. So if it's in Kannada or if it's in Telugu or Malayalam, so this may change. So what is the token? What it actually means? Let's understand with an example. Okay. So can you see the website here, which I opened?
Yes, yes.
Yes.
OpenAI tokenizer.
Right. So this is from OpenAI. Okay. So it is to better understand what tokens is and how it happens. Okay. So let's type up some sentence. Okay. So you want to suggest in sentence, Saurabh?
You can copy the one line above, learn about language model tokenization.
Great.
You can copy this word and let's see what it shows.
Okay. So yes,
Mm,
the number of characters is 39. Okay. But the number of tokens is 6. So number of words, let's say, learn about language model tokenization, right? So there are approximately like 5 words, 5 English
mhm,
words, but the number of tokens is 6. So how it is dividing it? Learn about language model tokenization. Tokenization is like divided into like one is token, the second one is assignation, right?
mhm.
And whenever we are interacting with large language models, so it actually doesn't count the words, number of words. It actually says the number of tokens, right? So the number of tokens being generated, the number of tokens that is being like given as an input. Let's just say a model has the capacity to respond like has the capacity for a single interaction, it can consume like 100 tokens. Okay. So if you give it a like structured input instructions with so many rules, let's say you are consuming already 90 tokens in the input itself. So it is allowed with only 10 tokens to respond back, right? So in whatever in its response, it's tried to adjust it to like 10 tokens. If not, after the 10 token generation, it just stops. Okay. So this actually happens like with many of the models because uh, for every interaction there is a token limit. So whenever your instruction like goes, like when you are copy pasting like 10 pages or 20 pages or 100 pages of PDFs, okay, if the model allows, most of the website models, that is, if you go for ChatGPT or Gemini, so it will restrict you. You can't input such huge token, actually. Okay, so whatever the limit is, right, it is to save the GPUs. So whatever if you give an input, the GPU will run, right? So since they are public models, they have to save their GPUs. So that's why they restrict the input of such huge lengths. Okay. So let's play with this statement here and try to understand how this token recognition changes. Okay. Let me make like learn into learning. Okay. Since it's just a single word. About into like language models. Let me just remove the space here. Right.
Okay,
So
divide
here,
it.
yes. It's considered like single word for
Earlier it
vectors.
was two tokens. Since we removed space,
Yes.
now it's three token.
Yeah, it is
Okay.
trying to recognize like with its training data, right? It has
Okay, okay,
recognized so
okay.
many words and it is trying to make sense of like make sense out of the input we are giving. So let's remove
Mhm.
this space. Now, as you can see, about there is L, angle is different, age is different, and model, right? So the tokens are still divided. When the word actually makes sense, it is clearly identifying the tokens as a single word, right? When
If
it
it's
is
a
merged,
small word, then a one token. If it's a big word, then probably two tokens.
not actually. Let's just
Uh,
say it is not about like being the word being big. It's actually being how does it make sense? So
okay. Is the
let's
complexity
just
of the word? Is it like a complexity of the word?
right. So
Let's say
whenever we are
uh,
using
the
English
general
words,
words are general English word could be one token, but if you use some specific kind of word which is difficult to understand,
let's say
then probably
dictionary
it
word,
divides.
right?
Okay.
Right. So basically, yeah, it doesn't work like that actually, Saurabh. So what it does is, so it has been given with all the English statements, English novels, English poets, poems, and English PDFs, all these Wikipedia stuff, everything, right? It is trained on all such. So
Mm-hmm.
whenever it sees some word which was already present in its training data and it has explored it like a lot many times, okay, it can easily identify that particular word,
Mm-hmm.
right? So that's why the learning it is not dividing the thing. But when I remove the space, it is trying to make sense out of like whatever it's been given. I'm trying to make sense out of it. Okay,
Mm-hmm.
that's what the agenda is about. So
Okay.
let me just. So as you can see, these were like completely. these words were making sense. Learning about language model tokenization. All the words are making sense, right? So the token considered was like they were as you can see, learning is a single token, about is a single token, language is a single token, right? It's a pure English. But when I merge these words, now this particular word is doesn't make sense. What does this mean? Maybe if I just Google, maybe Google may understand this, but
Nothing.
if I just look at it into dictionary, there is no such word, right? So it is
Hmm.
trying to make sense out of this particular word with the knowledge base it has. Like it knows English, so it is trying to make sense out of this word. Okay. So if I remove the space here, so now it is trying to make sense of this particular word. So what's the word? What could be this word? Right. So this is why the number of tokens are increasing because uh, from this particular word, it is trying to identify like all the patterns. So depending on its knowledge base, okay, where I could relate this. So that's what happening. Okay, it's not the complexity of the word; it's of like how that word makes sense is more of an importance.
And I see these tokens are depending on the models. So GPT
Yes.
5x is showing 6 token. If we go with any other model, the tokens will be less, I guess, or more.
Yeah, because yes. So this happens because as I said, like the identification of the number of tokens, the identification of these words are happening based on the training data, right? So
Yes,
for all these models, the training data could be different.
different, yeah.
Okay, even
The
though the
more
training
more
data
the
may be
training
same.
data, okay, the more the
Yes.
training data, the more an understanding and analyze it can do.
Yes.
Okay.
Yes. Okay. Depending on that, these tokens are created.
Mhm.
Okay. So
Okay.
whenever we are like giving an input, so these words are converted into the like number of tokens. Though the model looks at these tokens and it doesn't even read this English. So these English words are converted into like mathematical forms again, which we will look at into like further. Okay. But as of now, let's understand. So it doesn't understand the number of words we are providing. It understands only the language of tokens. Okay. And the token number of tokens and this making sense the number of tokens how we are looking at like learning is a different token about is a different token. This may be different for different models depending on whatever the knowledge base it carries. Okay. Yes. So yes, here is an example. Hamburger is a single word, right? So it may divide into like three words, that is ham, burr, and ger. Okay. So this can happen. There is no restriction with this. So why do we need to care about this? So whenever we are creating like any API interaction with a large language model, right? So it actually considers tokens. So we need to understand what tokens actually mean. Okay. So the context
Uh,
window usually
Arya,
uh,
this 128K token, is it a hypothetical number or
no,
it can be anything?
no. Actually, so 128 tokens is like usually 128 tokens are given to like most of the models. Okay?
Mm-hmm.
Most of the basic models allow like 128K tokens. Although the number looks great, like you may 128K, so it's more like 128K tokens, right? So that's huge,
Mm-hmm.
right? Although
Yes, yes,
these are the
yes.
numbers, these are just like whenever you are saying bike, right? So they may on paper be like 90 kmpl or 80 kmpl. On road, it is different, right? So
Mm-hmm.
similarly, uh, every model claims that it can consume like 1 to 8K tokens, and it definitely does. But the output quality decreases. So at least like if you have got like 30 to 40% of this particular maximum tokens, whatever they were mentioning, right? The output quality drastically gets down. Okay, this is the personal observation which I have done. Okay, so you have to be within like because this happens because there is something called it's like most of people who know AI may know context window. Okay, so the context window is how much interaction or how much information can the AI model actually remember before responding to my next request. Okay, I may have said it like my personal problems. I may have said it like my project that's been going on. I have said like what are the problems I'm facing, everything. So whenever I'm asking it let's refer back to that particular project I'm looking at. So let's solve this problem. So it has to get back to this project and take out that particular part and use it as a context, right? In order to respond. So how much can it
Mhm.
remember is nothing but the context window is. Okay.
Okay, for any particular task, first it generates a memory. Memory
Yeah.
like memory as in the storyline.
Yes.
Like let's
Yes.
say we want to do something in QA language. Let's say I want to automate some manual test cases. So
Hmm.
first it generates some story behind it, like what are the test cases. So that is called context window. Is it somewhat related?
Yes, you can say so. Let's say
Mm.
you have given it you have given the information of let's say in the text you have provided the information of this is the task one, so this is the test case one, this is the
Mhm.
information, this is the test case two, this is the information, test case three, this is the information. Okay, so you have given
Mhm.
like a number of test cases. Okay,
Mhm.
then you are asking a question, something like after 10 days you are coming back and you are asking a question. You explain a test case and ask it like have you explored this. Okay,
Okay.
now it should have this context, right, in order to answer.
Context, the memory. Yeah.
Yes. So this memory, what it can remember, what it can
Mhm.
hold on or look back at, is nothing but what we call context window. Okay. So when they say 128K tokens is a context window, it can actually hold on to 128K tokens. Uh, such window is accessible. Okay. But in practical, yeah, it is allowed to have 120K, 128K. So that's the maximum limit you can allow. You can definitely contain such. But whenever you are asking back, let's say you are filling up 120K tokens. Okay, if I have not reached the maximum 128, you have covered up 120K tokens. You have interacted something, and later you try to ask some question where in the initial. Uh, so let's just say you are into a single chat in ChatGPT, and you are trying to explain everything to it, and you are interacting it with a daily basis. Okay, after 10 days, the interaction would be like much larger, right? So let's say it has covered like 120K tokens already. Okay, so now
Mhm.
if you ask that ChatGPT something which was like discussed in day one or day five, okay, it may not remember it exactly. Although it is in the context, it may not remember it exactly. It may not reference its answer relating to that particular context you have provided. This happens because although there is a huge context window that's been provided, what so in order to save the GPUs, what these companies do is there is something called attention window. Okay, usually the attention window is of 10K tokens, 10K, 5K tokens for smaller models, or 2K tokens for much smaller models. Okay, so this attention window, what it does is it remembers only the past few, let's say, last 2 days interaction. So if it is a 10K tokens, so it remembers, it actually completely remembers only this last 2 days interaction. And if you ask something out of this, it may respond pretty well. But if you ask something out of 3 days back or first day interaction, it may not respond well because although it is in context, the attention window has gone already, right? So this attention window matters, but since the attention window is usually low, they don't market their models in by explaining the attention window. They market it by saying the context window. Okay, does that make sense?
Mhm. Yes, yes, yes.
Yes. So yeah, that was about context window and the API, and also all the API models. So all the LLM models basically. Let's just say OpenAI. Okay, OpenAI provide its own API, correct, to interact with its model. So if our application is making an interaction with this particular API, so every time the interaction happens, the number of tokens uh, input and the output tokens, it has got a cost associated with it. Okay. So why we need to understand the tokens? What it means is basically we have to understand there is a cost for input tokens, there is a for the response you are providing. Okay. This is user request. This is the response. So there is particular cost for this, particular cost for this. In order to better understand what does that, what's the estimation of the cost could be, we have to understand what actually the token means actually. So that's the main agenda of like why to understand the tokens. Okay. And
Yes,
here is
yes.
a new, yes. So
No, no,
any
no,
doubts till now?
no, no, no.
Any doubts from your end?
No, I'm good.
Thanks. Sure, yes. We will look at like one more new term. Okay, so that is vector embeddings. So this is interesting. So here is how here is where you understand how does actually the AI is understanding our language if it doesn't recognize our language anyway. Okay, if it doesn't process our language, so how does it happening and how is it relating particular request to particular concepts, right? So let's understand this. Let's get into this. Okay. So yeah, let me take up an example. Okay, let me take up an example. Okay. Let's just say there is a cat and there is a bird. Okay. Before this, let me take up a simple example. This is an x-axis. You guys definitely know number lines and the number
Mhm.
of dimensions, right? 1D
Yes,
through
yes.
2D, 3D, right? So let's just say this is an base 0. So this is a single dimension. So that is x, single characteristic. Okay. So let's just say x is nothing but marks of a single subject.
Mm.
Okay. I use
Okay.
there is a student with 10 marks. We will align it to 10, right? This is the point. Let's say there is a student with 20 marks. This is the point. Let's say student with 30 marks. This is the point, right? Exactly. So let's just say there are like two subjects now. Okay. So still this is an index. And let's just say in the second subject, y. So that user has got like 10 marks here also. There is other student who is 20 marks. Okay. The same student. Uh, so let's just say this first student who got 10 in X has got like 20 in Y. Okay. Right. And this person who has got 20 in X may have got like 10 in Y and 30, maybe something. Okay. So here, as you can see, in the single dimension, we were looking at a single character, right? That is a marks of a single subject. Understandable?
Yes.
And when we increase the dimension, we introduce like another dimension, that is y-axis, where we introduce another subject. Okay. Now we could define for the same particular student what his two subject marks is, right? It's for the same student, right? So
Yes.
this new characteristic, that is character 2, has introduced a new dimension through which we can actually mention where that particular student gets lies his marks, right? Let's just say there is a third subject, some z, right? This is three dimensions where usually so it's suburb, right? Length, breadth, and height. Okay, so 3D. Okay, three dimensions. So here I can ask of like third characteristic, that is third subject, right? Let's just say this user, this particular student in this case has got like fourth subject. Okay, we need to define a marks. So can we go for like fourth dimension, 4D?
Yes, yes. Like, and the
Definitely, right?
dimension is directly proportionate to number of parameters.
Right,
If there are five
exactly.
subjects, there are five dimensions.
Yes, yes. So similarly, let's just say I have to like create a dimensions for this particular classification. Okay, for a cat, can I say like let's say pause is a dimension. Okay,
Mhm.
so does cat have pause? Yes, they do, right?
Yes.
Does bird have it? No.
No.
Okay, and let's just say beak is my second characteristic. Do cat
Mhm.
have beak? No, right?
No.
Do bird have it? Right. Let's just
Yes.
say clause. Does bird have it? Yeah, they may. A cat have
Mhm.
it? Right, they can. Right?
Mhm.
Fur. Okay. Cat do have it, bird doesn't. Let's just say feather. Okay. There could be n number of characteristics, right?
Mhm.
So there could be n dimensions too. So if I
Yes.
scale this, there could be like n dimension. The number of characteristics is nothing but the number of dimensions. Correct?
Yes.
So if I draw this n dimension somehow, a cat and a dog may be like similar. They are mammals, they are pets, they have like four legs, they have fur, they have single mouth, they have two eyes, right? There could be like most of the characteristics could be same, but there are different characteristics, correct? So in this hypothetical space, in this hypothetical dimension, somewhere cat and dog could be like in a similar. It is more of like more of a similarity, right?
Mhm.
While bird may lie in different dimension, correct?
Mm. Yes.
King and queen may lie in like that's just a gender difference and the powers are same. So they may lie in some dimensions which is like more near, right? But let's say commoner, the social status, the acceptance rate, and all these factors. Okay, they may choose commoner to be like somewhere afar than like king or queen dimensions. Correct. So this the
Yes.
distance between these two dimensions could be huge. These 2 points in that particular dimension could be huge, right?
Yes.
Yes. So this is what we need to understand. Okay. I hope I gave you an analogy. So let's try to understand what it means now. So embedding is when I said the mathematical representation, right? So for every English word or English statement or every word, there is a mathematical representation. So this mathematical representation is nothing but these particular dimensions, whatever we are seeing, right? So these particular dimensions is nothing but the mathematical representation. Let's just say for this, I may write it as like x-axis, y-axis, z-axis, correct? In order to point out the subject values,
Yes.
right? So similarly, this is for student one. So for student one, I'm representing it to be like x, y, z axis and the values associated with it, right? So similarly, for n dimensions, I would have written, let's just say n is 20 for now. Okay.
Mhm.
So does cat have paws? Yes. Okay. So for cat, the first dimension could be like 1. Okay. They do have it. Okay. Most of the cats do have it. So most of the cats, I may have write it like 0.9 since it is most of the cat, not all the cats. Okay. The second,
Mhm.
beak. No cat will have beak, right? There are no species of cat which will have beak.
So
So
zero.
the second dimension could be 0. Okay. The third dimension, claws. Yeah, cat do have claws. Cat may not have claws too, right? So
Yes.
can I mark it to be 0.865 something, some number? I'm just providing an example,
Mhm.
right?
Mhm.
And there comes the fourth dimension, that is, it has got a fur. Not all the
Mhm.
cats do have fur. There are like where skin is visible. Those cats
Yes.
we have such breeds. So I may write it as like 0.76 something, some number, right? Where it is basically representation. It is representing the value within its dimension, right?
Okay, Arya, I just have a quick question here.
Okay.
Uh, when we were discussing about do cat have claws, do cat have fur, we are writing it, let's say, out of 10, 9 cats may have fur,
Yes.
one cat may not have fur. So we just
Right.
gave it 0.9.
Exactly.
Somewhere, if we want to relate, it's our training, like in since
Right.
childhood, what we are seeing. So,
Right.
likewise for the model also, is it depending on a training data, like out of 1,000 cat photos, 865 cat photos have fur and remaining don't have fur, so it come out to a number of 0.865.
Exactly. Exactly.
Okay.
Just like as we do, like as we observe our nature, observe our surrounding, and try to figure out particular conclusions. So these models are given with this particular data, right? So depending on the data, they are trying to configure something. They are trying to conclude. Okay.
Let's
So
say a model is trained with the cat images, and all the cat images were from a, let's say, a hospital or veterinary hospital,
right,
pet hospital. In that case, it will be very difficult to understand which cat is a perfect cat, because some
right,
cat may have legs, some may not have eyes.
true,
So
true.
with that kind of data, model will never be able to understand which is a perfect cat with a two
Yes,
eyes, two, yeah. So that all depends on the training data, I guess.
yes, exactly. If such models are trained, we usually don't use it.
Okay.
So yeah, so everything, the good model, the bad model, or everything depends on data. So data is the key. Okay. So that's why they say data is a turmoil of a new generation.
Yes.
So these dimensions, how these numbers are calculated, I'm trying to like give you an analogy, uh, a good understanding on how these mathematical representations are being created. Okay. So depending on the input, depending on all the training data, it has figured out some dimensions. Okay. This usually is not 20. So this may be 200. This may be 8,000. Okay. The dimensions could be like many. Okay. Depending on that, every statement you give in, every uh, like request you provide, okay, all those are converted into these particular dimensions are related to these particular dimensions, and depending on whatever the number you are getting, the mathematical representation, this is called vector actually. I was suggesting vectors, right? So this is what vector actually means. So this mathematical representation itself is a vector, and the number of dimensions is nothing but the number of coordinates. Okay, does that make sense? So these vectors, the queen vector and the king vector may have like similar coordinates. Similar, not the same. Okay. They may have dimensions which are like more of a similar. Okay. But king and commoner may have like way too apart dimensions. Okay.
Mhm.
So in this particular space, n-dimensional space, the commoner may be here, the king may be here. Since they are humans, they are not too apart. Since they are humans, they do have two legs, two hands, two eyes, right? It may be two apart, but compared to king and queen, the commoner is apart. Okay.
Yes.
So it has got its own dimensional model already. And whenever a user is writing a request, okay, let me know what are the major changes that's been happened in India, like for past 20 years. Okay. If that's the user query, let me just write it. Uh, Let me know what happened in India majorly for past 20 years. Okay. It checked through the statement, through it, through the number of dimensions. It may be like 8,000 dimensions. Okay. It is trying to convert this particular statement into the mathematical representation. Okay. This mathematical representation is passed down, and the model compares this mathematical representation with the knowledge base it has got. Where does this mathematical representation lies in? And from there, it gets the information, and now it tries to respond back. Okay. Since this mathematical representation would be similar with the knowledge base, like whatever the knowledge base it has got, the number of dimensions. So these particular coordinates could be of like similar, right? So that's why the information for king and queen are similar. Okay, there is a gender difference, but they are similar. Whenever we say when we say human, these are all similar. Okay, but when we say king, queen, and commoner is way apart, right? So whenever we are asking what are the powers king have, so this query may end up near to queen or king. Okay, and there it gets its knowledge base, and now it tries to respond, formulate a response. Okay, now this response is in English pattern, but the identification, the knowledge base that's been it is trained on, everything is coming from this mathematical representation, right? So how does it check internally what is which vector is similar? So where does it lie? We will check more on this, but yeah, with this explanation, you could have already understood now. So how this semantic meaning is understood from the query, or whenever we are providing a context, how this semantic meaning is being understood, right?
Yes, yes.
So yeah, so here we have taken like a supermarket analogy. Okay. So in the so let's say in supermarket, so there are like different sections, right? So there is a pharmacy, there is juice section, there is chip section, there could be like a grocery section, every such, right? So whatever we want, we will go there, we will buy it, and we will get back, right? We know exactly what products are there. Okay. So when we need, let's just say we need some snacks, we know it. These snacks lies in like snack section. Okay, that's how. So it has created its own dimensions, the model while training. Okay, so whenever the user request comes in and he asks for snacks, it exactly knows where the snack lies in, right? So that was the analogy here. Uh, Yes, maybe it's already like we have went for like 1 hour 15 minutes. Maybe we'll continue with this part 4, the transformer. We will get into transformer tomorrow. That's fine.
Yeah, sure.
Sure, sure.
Sure, sure. We'll check that tomorrow.
So then, any doubts like until now? So whatever we explored.
I'm a little bit confused about vector embeddings.
Okay.
I think I need to recheck the video again so that I can understand more. So for me, it's a little bit confusing. It's just in the beginning, so
Sure, sure, sure. Please look back, and if
sure.
it still doesn't understand, please do mention it tomorrow, and I will try to reopen like more example to it. Okay.